One side of the handout's very colorful with all kinds of bundt cake pans and stuff. Where did I put them? Here. Do we need that guy right there? I just want to do a review problem first, and then we'll do that last problem on that sheet. This paper's weird, but it's free, so I can't complain. All right, let me see. I sketched out a few examples. Yeah, let's do that. So what if I had this region to look at? Turn this guy on. Can you guys take a minute and sketch that out? Sketch it down. And remind me, what's x equals 0 another name for? The y-axis. I like it. So what can you tell me about this guy? Now that I factored him, what do you know? Just looking at it, what do you know? The what's are what and what? I mean, what can you tell? I factored it so you can see the what. Well, no, not x. That doesn't make any sense. It doesn't work for any number, but you can see the y-intercepts, right? I mean, what makes this 0? If y is 0. So x is 0 when y is 0, x is 0 when y is 6. Okay. Everybody, tell me, just from the beginning, you know what this looks like. What does this look like from the beginning? I know what that's going to look like. Be more specific than a U. What's it going to look like? Y equals x squared looks like this or this. So x equals y squared looks like this or this. Which one is this? Because the y squared piece is negative, it's going to be opening down. It's always hard for me to tell if you guys just want to share with me or if you really don't know. So, where's the vertex? I sort of just gave it away. If the y-intercepts are 0 and 6, the vertex has to be at y equal to 3. And when y is 3, what's x? No. 9. Yeah, just plug a 3 in for y. Right? That's all. Plug a 3 in for y, you get 9. That's why I made my scale all funkadelic. Now, to be honest, I'm being a little more detailed than you really have to be, but just because, just to show you all the little things you could do to help you get a sketch of the region. So I want to, and let's say I want to find the volume. If I rotate this around the y-axis. One big thing, all right. So today what we're going to do, some disk method examples. And then we're going to do the other method. So every time the disk method fails for some reason, not every time, but like most of the time, this other method, it's called the shell method, works. That's kind of nice, right? One reason this could fail is I need dx and I can't solve for y. Now here's the big thing. Disk method, here's the big thing. Disk method, if I rotate around an axis, the y-axis or something parallel to the y-axis, I have to have integral dy. The other method is the opposite of that. If I rotate around the y-axis or something parallel to the y-axis, it has to be dx. Why does this freaking make sense? Because what's the disk method all built on? Adding up what? What's the disk method built on? What do I add up? A bunch of whats? Circles, right? So if I do rotate this thing around, I'm going to get this funky, well, maybe not that funky, but oh well. And how am I going to find the circles? I'm going to find the circles along the y-axis. So like right here, this would be the circle. So I'm going to kind of slice this thing all along the y-axis. That's why for disk method, if I'm rotating around the y-axis or something parallel to the y-axis, it's got to be dy. Why does that match up beautifully with this function? This is a function of x or y. Y. It's a function of y. So that, thank God. So disk method should work. It's already a function of y. If I needed dx, I would have to solve that for y. I would need a function of x. Do you want to solve that for y? I hope to God you say no, because it ain't easy. To be really honest, you could. But it would be plus or minus shit, because you know there's going to be a square root. It would be quadratic formula in a way that you've never seen. So if you're interested, I'll show you, but I'm not going to just show everybody. Just screw that. Crap, we won't worry about that. Okay, maybe. So here's the big thing right now. Before we get into the other method, if I want to use disk method, when I rotate around the x-axis, or something parallel to the x-axis, the integral must be dx. So I better have a function that I can get in terms of x, or that if it's in x, I can integrate it. So dx, I want to rotate around the x-axis, dx. I want to rotate around the y-axis, dy. The other method, the shell method, is the other way around. So why is the disk method that way? Because if I rotate it around the y-axis, I locate my circles along the y-axis. So I move a little bit, get the circle, add it, move a little bit, get the circle, add it, move a little bit, get the circle, add it. I'm moving along the y-axis. That's where I'm going to find all my circles. So what will this integral look like? So what's the radius of, just draw yourself an arbitrary circle. What is this radius right here? What is the radius of that circle there? Oh, all right, no, I'm sorry, okay. An arbitrary circle. I'm putting it on the picture, but it's just anywhere it wants to be in there. What is the radius of this circle? How far does it go? Yeah, it goes out to 6y minus y squared. That's the radius. That's how far it is from the center. What's the center? What I'm rotating around. So the radius is always going to be from the center, for disk method, from the center out to the wall of my region. And what's the wall of my region? 6y minus y squared. That's the radius. Let's double check. Like you said, if I was at 3, the radius should be 9, and of course when I plug a 3 in, I get 9. What if I was at 6? The radius should be 0. And sure enough, if that's the radius, plug a 6 in, it's 0. So you can take a minute and just make sure that you define that correctly. You can actually see the circles and what they should be and just compare it. So each circle, what's the radius of each, the area of each circle? What's it look like? Area of each circle. So this circle I drew right there, what's its area? This circle right here, what's its area? It's the area of a circle in general. Pi r squared. And what's the radius? 6y minus y squared. Please understand that once we learn the other method, we have to kind of know when to use which method. It does get a little wonky, but the disk method is so beautiful. It's just a bunch of circles. So if I can identify the radius, I can immediately write the integral. I know what each circle is. It's pi times that radius squared. The really nice thing is if my function is a square root, the square is going to kill it. That's kind of nice. That happens sometimes. So what's my integral going to look like? It's going to be integral dy. How do I know that? Because I want to rotate around the y-axis, and I'm using disks. If I was using shells and I want to rotate around the y-axis, it has to be dx. I don't want that shit. I don't want to solve this for x. So let's not do that. So I can always put my pi outside because it's a freaking constant. No reason to mess it up in the middle of all my integral. And inside it's going to be r squared. Now to me, this is sort of the boring stuff. Just polynomial inside, there's 4 of that thing, and if you integrate a polynomial, I don't care that it's, oh well, too bad it's squared. I'm going to get a polynomial, easiest shit to do. Plug numbers in, right? So, and what's this from to, by the way? What's y? So this is always telling me what to look for. What's y going from to? 0, no. That's what x is doing, isn't it? That's what x is doing. 0 to 6 is what y is doing. I like it. This tells you what has to go here. It's in terms of y. What is y doing across that region? How did I know I wanted a dy? Because the function's in terms of y. I'm rotating around the y-axis. I want the thing that makes it dy. That's disks. And now I just have to, like I said, do this boring shit here. 36y squared minus 6y cubed minus 6y cubed, so minus 12y cubed plus y to the 4th, blah, blah, blah. I'm not even going to do that. Is that blah, blah yet or no? Is it blah, blah yet? How do you integrate this? What do you get? This one's nice because 36 has a factor of 3, because I need that 3 to come back up. So that's 12y cubed. This is nice because 12 has a factor of 4. Bring that 4 back up, so that's 3y to the 4th. And then this guy, too bad. From 0 to 6. So now we made that connection between antiderivatives and areas. If I find the antiderivative, I can then get the area by plugging in the endpoints. Hopefully you don't take this wrong, but I honestly don't care at this point. It's just a number, it gives a shit. Right? You just plug a 6 in. When I plug a 0 in, there's no e's or anything else, so it's going to be 0, so I don't have to worry about that side. So it's going to be whatever you get when you plug a 6 into all that business. How are we doing so far, you guys? So this is kind of a review of what we did last time. Now let me make one little change to the problem and see what that does to us. So it's going to be fundamentally the same problem. But let me make one little change. So it's still going to be bounded by x equals 6y minus y squared and x equals 0. Same region we're talking about. But now it's going to be rotated around, what did I want to do next? Yeah, x equals -2. So the region is the same region. The axis I'm rotating around doesn't change the region. I'm still talking about, just jump to the chase here, I'm still talking about this thing, right? But now where's my axis is going to be at, and my scale's wonky and I don't really care because I don't need this picture to be beautiful, I just need it to be useful. There's my axis of rotation, right? That is an axis that is parallel to the y-axis. So if I want to use disks, I need integral dy, and of course I still want integral dy because I have a function of y. So if this was a function of x, I would not want to use disk method. I'd want to use the other method that we haven't even learned yet. So what's going to change then? What's the only thing that really changes then? What was the radius in this problem? It was this here, right? Why? Because how far away from 0 is this wall? Well, it's 6y minus y squared away. How much further away am I now from the center? How far is this? That's the radius. Yes? So that the axis of symmetry, the axis is the center of my circle. That's what the circle is rotating around. So that automatically becomes the center. And what's the radius defined to be? The distance from the center to the edge. So watch how this is not a problem. What if I just drew the radius, right? What's the upper part of that? The bigger part is going to be 6y minus y squared, right? That's where it ends, minus where does it begin? -2. So then what's the radius? 6y minus y squared plus 2. And that should only make sense. If I take my axis back 2, now every radius is going to be 2 bigger. It's 2 further away now. It used to go to 0. Now it goes to -2. It's 2 further. That's why this makes so much sense. So on this specific problem, you didn't really have to write it like this. You could just put this. You know it's 2 more. Yes?
I know it's 2 more, but why did you subtract at the top? That's what I don't understand.
Because how do I find the distance between two things? Take the difference, yeah. And that, of course, is why mathematically it becomes +2. But I agree with you. On this problem, I didn't have to be that specific and that formal. But I'm trying to get you ready for when things are a little bit wonky, like the next one I'm going to do. So try to take a second and set up what the integral would look like for this. It looks exactly like it did before, except a different radius. And this time we're really not going to do it because I feel like multiplying all this shit. So y still goes from 0 to 6. The only thing that really changes is my radius is now a little bigger. So how would you do that integral? What would you have to do first? Special place in my heart for the people that just integrate the inside and then make that 3 and shit. I mean, that's complete bullshit, right? I mean, what do you have to do first? Do you just not want to do it? Is that why you don't want to say it? We're not going to do it. I already told you we won't, but what would you do? You would just square this out, right? Get this big-ass polynomial, go to town, just like we just did a second ago. I like it. Integrals are not allowed to do the inside of a function. That's not how they work. So a really quick side note. This problem is not like overly difficult, but if you're like me, and this is fine, this is not a hard problem. If I have to do it on a test, I'm going to freaking do it because I want the freaking points. But why is this a little gross? I got 3 things, and if I write it next to itself, I got all these freaking distributions to do. Oh, well, right? Why? So that would be what you do for that integral. Should be easy. Foil that thing out. Foil. I love foil because now it should be more than just first outer and last. But foil that thing out, integrate the polynomial. That's easy as hell. And then plug shit in. Right? That's all you have to do for the rest of this. Just a side note. This has nothing to do with this problem. But if I had this integral to do instead, why is this integral easier? What do you got, Jeff? This looks like it should be harder. Can anybody tell me why that integral would actually be easier? What's the derivative of this? What's the derivative of this? 6 minus 2y. That's what this is. U sub works. There's a derivative of something that's stuck somewhere in the integral. So I could actually use U sub on this. And that's really cool if this is a 20th power. 20th power. You want to write this 20 times? Multiply the first 2. Now multiply that by the third one. Holy shit. So thank God U sub exists so that I can do this problem pretty damn easy now, since the derivative of the stuck function is in there. All right, but again, I want to make sure you understand, this has nothing to do with this. This is just a separate. If you saw this, it would be easier than this, because I actually don't even have to do that in this problem. I could just use U sub instead. Okay, just want to point that out. All right, is everybody cool? Everybody understand that this should be easy? It's just square that thing out and integrate. That's a nice polynomial. Should be easy. Okay. All right, so let me mess this up one more time. Same region. So hopefully you're not tired of the region here. Bounded by x equals 6y minus y squared and x equals 0. Rotated about x equal to, what did I say? It doesn't really matter. Yeah, sure. Try to sketch that. Try to put the axis of rotation in there, like I did. There's the one we just did. There's the rotation axis. Try to sketch the region and put the rotation axis in there. We already have the sketch of the region. It should be. Bang. Let me catch up to you guys. So of course it's just going to be 0 and 6 and then out somewhere a little bit here. Now I want to go around. Oh, shit. Make one change here, guys. Hopefully you guys understand. Where does this go out to? 9, right? So let me make this, doesn't really matter. Let's make this 13. I can't put my axis of rotation in the middle of the region because then it kind of like overlaps on itself, and that gets really funky. If I rotate it around an axis through the middle, it's going to overlap itself. All right.
Are we not covering this here?
Say again?
Are we not covering this here? Are we not covering this?
Covering what?
This overlap
if you have a problem where the region needs to be overlapped, that doesn't make physical sense. Now, that still could be a valid thing to do, but then there's a consideration about, well, if you do start to go through an area that already exists, do you double count that? Do you only rotate halfway? Do you see what I'm saying? So that kind of opens itself up to, well, what situation means you do it this way? What situation means you do it that way? We don't have time right now to do that. It's not a part of this section. So I was not careful enough when I picked my number. 3's in the middle of this stuff. If you try to rotate it, doesn't it kind of hit itself? You're not just rotating, you're actually leaving it here. It's opening that thing up and then it kind of like goes through itself. All right, that doesn't make physical sense anymore. This is supposed to be physical volume for right now. Okay, so if I go around 13, let's go around 13 instead. See if you guys get this. This will be a nice one so I can check what I get. So now it's going to, now you don't have to do this ever, but I mean, it's not a bad idea because it doesn't have to be beautiful, but this is basically what it's going to look like when I rotate it, right? It's going to be this big, funky, nuclear power plant looking thing. Do you guys see that? If I rotate that region around, it's going to be like that. Hollow in the middle. Discs will still work. Well, what's the radius now going to be? That's what my whole focus is for disks, is what's the radius. So for some arbitrary location, what is this distance? Right there. That's the radius. What is that distance? Well, where does it go up to? 13. Minus, where did it start at? Yes. So I want you to see the connection here. This one was, that was the top minus this, to see how far away it is from that. Now, this is the top, 13, minus that. And tell me, right here, what should that number be for the radius? What is that? Right there. How far apart are they supposed to be? Right there. Because that goes out to what? That goes out to 9. That's 13. So how far apart are they? 4. So when I put a 9 in here, when I put a 3 in here for y, the answer should be 4. And of course it will, because when I put a 3 here, I get 9. 13 minus 9 is 4. Just make sure, if you just do that one quick little check, pick a place where you know what the radius is supposed to be. Make sure what you just wrote down works, because otherwise you can tell when you put things in the wrong order. But it's always going to be whoever's bigger minus whoever's smaller. The wall or the axis. Bigger one minus smaller one to keep things physically making sense. Negative radius is freaky as shit. We don't want to do that. So then my integral is going to be the same damn thing again, right? It's going to be integral 0 to 6, put a pi on the outside, radius squared. So if all I'm doing is moving my axis of rotation, everything stays the same except the radius is altered a little bit. It's getting bigger or smaller. Okay, maybe. All right. So let's finish up this other sheet, and then I want to do one more thing here that will lead us into the shell method. I'm not going to teach you how to become a grifter and cheat people out with the shell game. Yes?
Can you go back to the previous sheet?
This one here?
Yes. So when you were giving us a side note earlier, and then we saw that there was a derivative of another piece inside the function which we can just use substitution for. Now, if that function was factorable, can we do something similar to that?
Yeah. Sometimes factorable functions lead to easier ways to do it, sure, but not very often, to be honest. It'd have to be a very special function where the one factor is somehow directly related to the other factor. Does that make sense? But It's just another thing to kind of look for if you have a problem. You're like, I don't know what the hell to do with this shit. Well, one, is it factorable? Maybe that leads to something. Yeah, and trust me, for those of you that go on to Calc 2, that will become a major part of one certain type of integral, at least one. Off the top of my head, the trig sub that I talked to you guys a little bit about before, that just sounds so fantastic. No, not really, but it is fantastic. Okay, is that cool?
Yeah.
Okay. This is where, you got to learn what integrals mean. You got to learn the basics of integrals. You got to see the connection with areas, and then the antiderivatives, and then the u sub. But then you start to say, well, what else? If a factoring, will that lead to something? We'll try it. You start to kind of broaden what you can try to do on a problem. That's the whole point, is you keep getting more and more tools to try for any specific problem. So that's the very first thing Calc 2 does, is say, all you got is u sub so far. That's the only real tool that we've got, to be honest. That's it. And there's a lot of integrals that won't work just with u sub. So then you start to go, what else could we do? What other substitutions or reorganizations could we do? Okay. So here's, we did all the parts of this except this last problem. So let me give myself a fresh one. Everybody's got this, right? You check that around. So first off, just try to sketch that region and then put the axis in. The axis B. Oh. Okay. This is what I get. So there's my backwards parabola. There's my, if you solve for y, just to double check and make sure you get the slope and the y-intercept. We're not used to think of it in terms of run over rise. That's what this would be. We're used to think of it rise over run, which is what that would be. So there's what it looks like. That's the region. There's some extra shit here, but oh well, I just didn't know where they're going to meet at first. I don't even have to do the algebra to see where they meet, because I could see where they meet just by what I've plotted. But just to double check, how would I do the algebra to see what these intersections are, just in case I don't really trust my graphing? What do I do? Set them equal to each other. Negative y squared equals negative y minus 2. So y squared minus y minus 2 equals 0. And then you can factor y minus 2, y plus 1. So they should meet at y equal 2. Bam. And y equal negative 1. Bam. So that's where they meet. Kick ass. To be honest, very often when I do this kind of problem, I don't know why I didn't do it here necessarily, but I do that first, and then I use that to help me graph each thing, because I already have 2 points for each then. So, if I'm going to use disk method, let me see if you guys get this. It's going to be integral d what? Is the axis I'm rotating around parallel to the y-axis or the x-axis? All right, I'm going to answer that for you. Maybe it's the y-axis, right? It's parallel to the y-axis. So then I want this to be dy. Does everybody get that? Because that is going to make this so much easier. That's almost the first thing you want to do because that governs everything else. If I want to use this method, this has to be dy. Why does that look like a good method? Because the functions that are given to me are functions of y. Okay, that seems to check. So all I got to do now is figure out what the radius is. So I just pick an arbitrary place here. Now what method am I really using here? Because if I rotate this thing around, is it going to be solid throughout? Or is there going to be hollow parts? Let me say it like I did last time. Does the region I'm rotating, does it hug the axis I'm rotating around? No. So what method am I really using? I'm still using discs, but I'm just going to subtract 2 discs. Is what the book calls washers, right? So I'm going to have to get an inner radius and an outer radius. So what's this inner radius going to be? What's it go up to? It starts here and goes up to here. What's this one? What's this? This is x equals 2, right? So the inner radius is going to be 2 minus, what's this? This is where the inner radius stops. That's inner because it goes to the inner wall. The outer radius goes to the outer wall. That's crazy. So 2 minus this wall, of course, is negative y squared. So 2 minus negative y squared is 2 plus y squared. That's what our inner is. And what's our outer? It's going to still start at 2. 2 minus this wall. And this wall, of course, is negative y minus 2. 2 minus all that makes it all positive. Where'd that extra thing come from? 2 plus y plus 2. So 4 plus y. That's my r outer. So how do I find the area of the shaded region? If this is 1 and this is 4. You see what I mean when I say this is cookie cutter problem? Not that it's a problem that you can cookie. No, this is a physical cookie cutter problem. You got dough and you're going to cut that middle one out. Looks like Happy Pac-Man, but it won't. How do I do it? You do exactly what it physically sounds like you do. You have a big circle, and you're going to cut the little circle out. So you're going to take the area of the big circle, minus, for cutting, the area of the small circle, right? So it'll be 16 pi minus pi. Pi r squared minus pi r squared. So what are we doing right now? The same thing, believe it or not. For every position on the y-axis, I'm getting this picture. If I look from above, I'm getting that. I'm getting a hollow middle, and then a filled-in middle part right here. So what I'm doing up here is I'm going to do the integral pi r outer squared minus pi r inner squared. The outer one squared is the inner one squared. So I get the area, the difference of the areas. I get the area that's left. So right here, this is going to be pi integral. I know it's dy, And what's y going from to in this problem? Y is going from -1 up to 2. Right? -1 to 2. The inner radius is there and the outer radius is there, so it'll be our outer, the big circle, minus the small circle. And then again, the rest of this is easy. It's a polynomial inside. You got to FOIL those couple things, get your like terms together, integrate. So setting up the integral is going to be the difficult part. So it's that rough sketch that is going to help you out. And the worse you are at doing that, the harder some of this is going to be. I want to come back to that problem we were doing and just show you one more thing to kind of transition us into shells. So if you're tired of this region, it's too bad. So bounded by, what was it again? Where did I put my other stuff? There we go. X equals 6y minus y squared, and x equals 0. So it's still that same region, but now if I want to rotate around the x-axis, so still that same region, and now I want to rotate around the x-axis. This would so desperately suck if I want to use disks then. Can somebody tell me what that immediately says I need for the integral? So rotate around the x-axis. The integral would have to be with respect to what variable? dx. So right there, if I want to try to use disks, it has to be that, because it's always, for disks, the d part matches with what I'm rotating around. From rotating around something like this, it's dx. Like this, it's dy. Which is why the other method works when this one fails, because the other method is the reverse of that. And we're going to get into the physical reason why that is. But just on the surface, that makes sense. If I had another method, that would, like, why does this suck? What do I need inside then? I need a function of x. And what did we talk about earlier? Do you want to solve this for y? No, I don't. I could, but it would so suck. And let me see if you guys see this. This is one function of x. This is the positive radical business, and this would be the negative radical business. So not only would it suck to just solve it in the first place, but then you have two different functions to work. Oh, you have to break your integral. Oh, no. All right. So this is kind of like the motivation for this other method. Now, but before I go to this very complicated looking part, I just put all kinds of information. Before we go to that one, I got a little intermediate step part. Guess we can see a bunch cake pan on this one, for sure. All right. So the last problem probably would be kind of disgusting. So I want to give us one that's a little bit easier to work with to step into this. So I kind of gave you the picture down here. Don't write anything on there yet. Let's just give ourselves a rough picture. Wow! Good old Moby Dick there. Hope like a snow hill. So it's between this. And, of course, that means what? Y equals 0 means the... Y equals 0 is another name for the x-axis. I love it. And I want to rotate around the, what does that say? Y-axis. Okay. So I actually want to rotate it like this. Right? So what would discs, if I try discs would require me to have d what here? I'm rotating around which axis? The y-axis. So discs would say integral dy. I like it. Let me say that again, because this is huge. This is the part that my teacher, when I took this, never really explained fully. That's why I kind of hated this at first, but now it makes so much sense. Disc method is the one that the integrals variable will agree with the axis I'm rotating around. So if we're rotating around the y-axis or something parallel to the y-axis, the integral has to be dy for disc method, and vice versa for the x-axis. So get that in your brain for the disc method. The shell method is the reverse, and we're about to get into the physical reason why that is true. So why is that true for disc method? Because how do I find my circles is along the axis I am rotating around. If I move around this axis, I get another circle. Move up a little bit, I get another circle. That is the physical reason why the integral has to be dy in this case for discs, because I'm rotating around the y-axis. Okay. So I locate the circles along the axis I'm rotating around for discs. Why does that suck for this problem? This one is like basically impossible. Not really, but I mean, basically. What would I have to do then? I need a function of what in here? Y. I have a function of x. Do you want to solve this for x to get a function? No, I definitely don't. The other one is doable. This one is, you don't want to do. You guys kind of with me? So if I gave you this and it said solve for x, you should come up and just kick me in the shin and say, that ain't happening. Yes?
So is there about the x and y axis just dy dx? What if it's like the example where you said like x equals?
Okay, so again, I try to be really careful with, if I go around the y-axis or anything parallel to the y-axis, it's fundamentally the same thing, that would have to be dy. X-axis or anything parallel to the x-axis, dx for discs. This other method, then it kind of makes sense. If I was going to make another method, I'd want to make a method where I could do the opposite of that for situations like this. So I don't want to use discs then. I can't. I cannot, because I'd have to be able to solve this for x so I could have a function of y in here. I don't want to. And sometimes it will be impossible to do so. This one, it's almost possible. It's gross. All right. So look at this. This is too, all right. I know I keep saying that, but this is really, really, really too beautiful to believe. So here's the idea with this one. If I was going to, I know this isn't my region, but this is the best example I could find, so I didn't have to draw it myself. If I was going to rotate this around the y-axis, for example, one way I can think about doing this, instead of trying to add up a bunch of circles, what I could do is I could put a rectangle that is sitting on the axis that's perpendicular to what I'm going to go around. So when I do rotate this, I get this shell. So of course I would rotate all the way around. That's a little hard for me to draw. So I'm gonna get what I'm trying to draw right now is like half of this picture. You see, I get this shell. For every rectangle I could imagine, I would get another shell. So how would I get the total volume of the whole region rotated? I just add up all the volumes of these shells. So now we got to stop and think. So let me stop right there for a second. So this one's really nifty. The other one was circles that the circles line up and they create this shape. It's almost like if you ever watch 3D printers. They kind of do it that way. This is actually a chunk of the volume. It's a bunch of shells. And then I would have another shell. Like if I did this one, I would have another shell on the outside here. And another shell, and then I would end up with this picture. It shouldn't have been taller, but too bad. I can't draw worth shit. Sorry. So there's a shell, and then if I add up all the shells, I end up with that picture. I think the book has a decent little picture of this. Well, they do there. Where are you? Here we go. This one's going around this is the same image. Oh, there you go. That's where I stole it from. So here's all the shells, kind of like, well, not all of them. This is a finite number of shells because I used a finite number of rectangles. And then in the limit that I use an infinite number of rectangles, I end up with this. So instead of adding areas of circles, I am now going to add volumes of shells. So a really good thing to look at right now is what the shit is a volume of a shell, right? What do I need to know? It's like for this guy right here, this shell. Let me see. Am I feeling adventurous? Why not? Let me try to draw him down here. So I got this Campbell soup can, but it's empty, right? And there's a little bit of thickness to it. This is where I'm going to have some trouble. That's too bad. Oh well, okay. That's terrible. That's not too bad for me. Anyway. So let's just take the Campbell soup can, because all I'm going to do at the end, if I can get the area of this, I would just have to multiply by that thickness to get the real volume of that shell. All right, so let's just take a step back. Let's just look at like if I took the label off of a soup can, and let's say this is R, right, and this is H. How can I get the surface area of that label? Yeah, you slice it, open that bad boy up. It's now a rectangle, because if you take a rectangle and fold it, it becomes a cylinder. The height, of course, is H. What is this? That would be this, because if I slice it and open it up, this straightens out. Well, what is this?